Hello and welcome back. In the previous video, we added curves to our turning animations. In this video, we're ready to use this data in order to help us to rotate our root bone towards the direction of our controller, which is where our camera is facing, in order to have our character rotate while the animation is playing. So let's get started. Here we are in shooter_anim_instance.cpp, and we've got these on-screen debug message calls that we used to see what our root yaw offset was equal to, and also our character yaw as well. And we saw that root yaw offset and character yaw were the opposites of each other. They were the same value with opposite sign. We don't need to use those anymore, so we can go ahead and remove those. Now also, we saw that we took root yaw offset and subtracted yaw delta from it. I'd like to be safe and make sure that this is clamped to a value of -180 to +180, so that way nothing actually gets out of this range. So I'm going to add a comment here and say root yaw offset updated and clamped to -180, +180. And in order to clamp this like that, we're going to use a function in uKismet Math library. So we're going to no longer use a minus equals, we're just going to use equals, and we're going to use uKismet Math library, and the function is called normalize axis. And normalize axis is going to take the following. It's going to take root yaw offset and subtract yaw delta. So we're taking root yaw offset, what it was last frame, we're subtracting off yaw delta like we did before, but normalize axis will clamp it to between -80 and +180. So it'll never be less than -180 and it'll never be greater than +180. And then we'll assign that result back to root yaw offset. So it's essentially the same thing as what we had before, only now it's clamped. So it's safer. Now we're going to check to see if our metadata curve is going to return 1. That metadata curve we created called turning in the last video will return 1 if we're playing the animation, but it will not return 1 if we are not playing the animation. Just to remind you, here in idle turn 90 left trimmed, here's our turning metadata curve, which I said is only a straight line at the value of 1. So we're going to get that value from the metadata curve. Let's make a const float, and let's call this turning, and we'll initialize this with the value that we get when we call get curve value. So get curve value is a function that takes a fname, and we can use a text macro here. And all we need to do is provide the name of the curve. We called this curve turning. So here in the shooter anim instance, the anim instance class has access to this function called getCurveValue. It simply takes an fname. We can provide the text macro with a string with the name of the curve that we created. Now this will be 0 if we're not playing an animation that has the turning metadata curve, but it will not be 0 if we are playing the animation, so we can simply check if turning is greater than 0. And here just above it, I'll add a comment saying 1.0 if turning, 0.0 if not. Okay, so now we're ready to get the curve value from our rotation curve. Now we're going to add a couple of member variables for our rotation curve value. So let's go to shooter_anim_instance.h. So let's make a float value called rotation curve. And I'll give this a comment saying rotation curve value this frame. And we'll add another one for the value last frame. So we'll call this rotation curve value last frame. And the comment will say rotation curve value last frame. Now back in shooter animinstance.cpp, we can get this value inside the check if we're turning. So we can say rotation curve is equal to get curve value. And remember, curve value takes an f name. We can use a text macro. And we called this curve rotation. Now, before we set this, we can set the value from last frame into rotation curve last frame. So rotation curve last frame is equal to rotation curve. And we want to get the delta. And let's see what I called it. Looks like I called it rotation curve value last frame. I'm going to take value out of there because that makes it unnecessarily long. Okay, so rotation curve value last frame equals rotation curve. Then we update rotation curve and get that value from the curve. And now I'd like to get the delta. I'd like to get the difference between the curve value last frame and the curve value this frame. So we'll make a const float delta rotation, and I'll initialize this with the delta. It'll be rotation curve minus rotation curve last frame. So this will be the difference between the rotation curve value last frame and this frame. So let's take a look at this. Here's the rotation curve. So let's say we're on this curve and we start off at this key value, which has a value of -90. And next frame, we move a little bit further along. We're about right here. Now, this curve value has a value of -86. Now, if we take the current curve value and subtract last frames, then we're taking a negative value and subtracting a larger negative value, and subtracting a negative is the same as adding. So this is going to be a positive value, and it's going to be some small change. You see, we're going up in value, and so this will be the amount that we've changed on this curve. Okay, so we have this delta rotation. Now we want to use this to compensate our root yaw offset. Basically, we want to see if our root yaw offset is positive or negative. If root yaw offset is positive, then that means we're turning left. So let's make a comment to remind us. If root yaw offset is positive, or in other words, greater than 0, then this means we're turning left. If root yaw offset is less than 0, then this means we're turning right. If root yaw offset is positive, it's greater than 0, then that means we've rotated our camera towards the left and we've been pushing our root bone towards the right. Our root yaw offset needs to be subtracted from. And what are we going to subtract? Well, we're going to subtract this delta rotation amount, the amount that our curve has changed since last frame. So let's use the ternary conditional operator. So let's say if root yaw offset is greater than 0, then this means we're turning left, and we can take root yaw offset and subtract off delta rotation. But in the other case, if root yaw offset is negative, that means we're turning right. Root yaw offset is negative, and we need to take that delta rotation value and add to root yaw offset. So we're going to add instead of subtract to root yaw offset. So root yaw offset plus equals delta rotation. And in the else case, we're turning right. Now, if you ever see something like this, where we have an if case, and we check a condition, and we do something if it's true, and we do something else if it's false, that's the perfect opportunity to use the ternary operator. The ternary operator looks like this. First, we have our condition. Root yaw offset is greater than 0. Then we have the question mark. And what follows is the action we want to perform if our condition is true. So that would be root yaw offset minus equals delta rotation. Then we have a single colon, and what follows after that is the action you want to perform if the condition is false. That's root yaw offset plus equals delta rotation. And then finally, our semicolon goes at the end here. So that's the use of the ternary operator. If you haven't seen it, it's exactly identical to this if-else statement. You can use either one, but I like the ternary operator because it's concise and it doesn't take as many lines. So we can go ahead and remove this, but I thought I'd show you both ways. Okay, so now our root yaw offset is going to be subtracted from if we're turning left, and it's going to be added to if we're turning right. And the amount we're adding is the delta from last frame of our curve value for rotation curve. Okay, so the last thing we need to do is see if we've rotated too much, because if we rotate too fast, then rotating by 90 degrees isn't going to be enough. We need to see that excess amount that we've rotated and subtract from root yaw offset so we're not pushing the root bone back in the other direction too much. We need it to catch up. So we're going to create a const local float called absolute or ABS root yaw offset. So root yaw offset. And we're going to initialize this with the fmath function abs for absolute value. And we're going to pass in root yaw offset. So this gives us the absolute value of root yaw offset. And we're going to see if that's greater than 90. So we're going to check if abs root yaw offset is greater than 90. If that's the case, then we can get the excess. So const float yaw excess. And that's going to be ABS root yaw offset minus 90. So we can check to see if root yaw offset is positive or negative, and then we can subtract or add yaw excess just like we did up here when we subtracted or added delta rotation. So we're going to say if root yaw offset is greater than 0, question mark, root yaw offset minus equals yaw excess. And then, of course, we'll use the single colon and say root yaw offset plus equals yaw excess. Okay, so what this is doing is we're getting the absolute value of root yaw offset, and we're seeing if that's greater than 90 degrees. If it is, then we need to compensate for that by taking the absolute value minus 90, that's the excess amount, and we'll subtract that off if root yaw offset is positive. That means we're turning left, and that way we'll allow the root bone to come closer to our actual camera direction. So we can go ahead and compile this. Okay, so we're back here in the editor. Let's give this a try. So we'll go ahead and turn our camera by 90 degrees, and there she turns to the left. We'll turn back 90, and she turns to the right. We'll keep turning 90, and you'll see that she compensates once we've rotated by 90 degrees too many. And of course, if we just jerk the camera all the way around, then she'll catch up. She'll keep turning until she gets to at least within 90 degrees, and then we'll have our camera basically in this 180 degree window. So we're able to turn to the left and to the right. Now, notice there's still a couple of issues here. For one, if we reload, then it doesn't quite work correctly. It's not going to turn while she's reloading, so we need to fix that. And also, if we turn just enough to where we don't quite trigger that animation yet, and then we start running, you'll see that she's not running in the right direction. She still stays forward, and then when we stop running, it turns her. So that's another issue. So we need to fix that. So here in the turn in place function, you'll notice when the speed is greater than 0, we don't want to turn in place. But the thing is, if we've already turned in place a bit and then we start running, well then our root yaw offset is going to have a value. and we're still going to be offsetting our root yaw by root yaw offset. So if speed is greater than 0, then we simply want our root yaw offset to be 0. So we're going to set it equal to 0 here. So root yaw offset equals 0. Now, we also have a character yaw last frame, which we're only setting in the else case if speed is not greater than 0, which means if character yaw last frame has a value and we start moving, then it's going to keep that value. We're not going to reset it. So we need to actually set this character yaw last frame equal to the character yaw value this frame if we're moving. That way, if we enter into the else statement again, then we won't have data from the last time it was saved. We'll just have it zeroed out, so yaw delta will be 0. So we're going to say character yaw equals, and we're going to basically use this line here, shooter character get actor rotation dot yaw, and we're going to set character yaw last frame equal to character yaw. That way there's no delta between them. And we're going to also set our rotation curve and rotation curve last frame equal to 0 as well, so there's no delta between those. So we're going to say rotation curve last frame equals 0 dot f, and rotation curve equals 0 dot f as well. So this will zero out everything when we're running, when we're actually moving. So go ahead and compile that, and while that's compiling, let's hop back in the editor and we'll go into shooter and BP, and let's take a look at the reload. So if we go up here, we have hip to aim with reload, and this gets our cached hip to aim, runs it through the reload slot. Now we only want this reload to be on the upper body. And if you remember, we had a layered blend per bone a little higher up where we had our cached locomotion and cached weapon fire. That's the cached locomotion going through the weapon fire slot. And so this is doing the layered blend per bone where it's only using the cached weapon fire pose for the upper half of the body. So we can actually just run this through the reload slot, and the reload slot will only apply to the upper body. So if we drag off of this and type slot, and we take this slot and we set it to the reload, then we'll run that into the blend pose, and then we don't need to use the reload slot down here. So here where we're taking cached hip to aim and running it through the reload slot, we can just skip this step altogether and just use cached hip to aim down here. So instead of using cached hip to aim with reload, we can just simply use cached hip to aim. So use cached pose, cached hip to aim right here. So we don't need to use cached hip to aim with reload anymore. We can actually take this whole part out. So now we don't have that section anymore. We're just going to use cached hip to aim when we're feeding it in to rotate root bone. So we can compile that, and let's give this a test play. So here we are, we're rotating, that looks good. And if we reload and we rotate, you'll see that we're still doing the rotation and we're still playing the rotate in place animation. So that looks good. Now we can also still fire, and as we're rotating, we can still fire. Okay, so that's going to conclude this video, and in the next video, we will continue developing this system. We'll see you then.